is the first two stages are pretty similar across all implementations. Now, the individual characteristics of each language start coming into play. So, the first two stage, which is scanning and parsing, are the proven path of the language designer that we were talking, where the compiler or the way you compile a programming language is basically these two paths. So these two paths are the proven, the classic ones. At this point, we know the syntactic structure of the code. Things like which expressions are nested in which, but we don't know much more than that. So at this point, after we scan the token and then get or parse it into a tree, we now know the nested structure. So if you do not know, like in a language, in a sentence, those are actually nested because you have the top root, which is the sentence. Inside that, you have nouns and verbs that root to each other, right? Some verbs depend on other first noun, and some noun depends on the second verb. It's the same here. In an expression like a plus b, we know we are adding a and b, but we don't know what those names refer to. Are they local variables, global? Where are they defined? So this is where most people trip off, because this is where the tricky or the sophisticated part of compiler, where you don't just need to determine the sentence or the structure of that, those are the easy parts, but where those sentence apply, like those meaning, like in words, especially in a human language, the meaning, you can it's a lot of meaning in one sentence. People take different meanings in one sentence. That's why we also have different religions, right? And different interpretation of Bible, or different interpretation of that. So it's the same here. So how would we structure a rule, or what's the proven design pattern that will allow us to structure a rule to define that? We will discuss that here as well. So the first bit of analysis that most languages do is called binding or resolution. For each identifier, we find out where that name is identified and wire the two together. So the first bit of analysis, after we have the tree structure and the token, is we bind that or resolving it. So later we will have a resolver class that meant to identify that variable or that expression and into which environment it is located. Is it local, global? So another thing that persists over time, aside from the first two steps, the parsing, the scanning and the parsing, or the lexing and the parsing, is the resolution. The global and local, and the resolution word. So this is important because these are the basic that allows you to minimize this complexity, to be able to achieve our output goal, to understand compiler, and therefore make better decision in our code. So this is where scope comes into play. For each identifier, we find out where that name is defined and wire the two together. This is where scope comes into play. The region of source code where a certain name can be used to refer to a certain declaration. So this is where, when you create a variable or define it, sorry, this is where you reuse the variable basically across regions of the code. So it's related to the source code we were discussing when we create a logic or program, or when we teach the computer what we want them to do. So this is the part of the source code where the compiler or the interpreter rather that will interpret the code will bind that to that specific section you meant the computer to do. If the language is statically typed, this is when we type check. So, in a statistically typed language like TypeScript, this is in compile time because we're resolving those variables. We make sure that their values are in the right place, they identify in the right environment. So once we know where A and B are declared, we can also figure out their types. Then if those types don't support being added to each other, we report a type error. So as you can see, this is also where the error that we will create, or that we already create in the first part of the implementation, which is scanning and parser, but not fully implemented yet because the program is not running. You cannot return an error why the program is running, but like doing some helper on that part will be needed for you to implement a return of error in the runtime or in this third step. So this is also where we return an error if the value, or once we know where A and V are declared, then if those types don't support being added to each other, then we report a type error. So this is the semantics part. Like if those values don't really allow by the language, um, you can't really teach or the program like that in that language. Therefore, there's an error that the interpreter will provide to you because an interpreter will scan the characters and then the numbers. So they will scan that and then they will here I'll just show you. They will scan that like this using a case, switch case. So they prepare that case for string case. So for string we prepare via switch and case, and then for character we prepare via for numbers we prepare via if else. So we just do a while loop, and then once we counter an error we break. So unexpected character. So these are the metadata that we'll be using to get or to return an error later. So the language will build in this book is dynamically timed. So it will do its type checking later at runtime. So take a deep breath. We have attained the summit of the mountain and a sweeping view of the user's program. All the semantic insight that is visible to us from analysis needs to be stored somewhere. Often, it gets stored right back as attributes on the tree, on the syntax tree itself, extra fields in the nodes that aren't initialized during parsing but get filled in later. So now we're on the top of the mountain that we can now see what's the program or the user or the programmer actually mean with their code. Now we can now take a deep breath, but those all semantic insight that will help us when executing the app using the CPU, converting it into manual calculation, is that we will need, often it gets stored as an attribute. So it's stored in the tree as well. So it's another node in the tree. Remember, tree is a node data structure. And then only initialize and get filled later at runtime. Now, oftentimes, we may store a data in a lookup table off to the side. So, like a lookup table with an operating system. Remember the operating system where you have a process tracker where it tracks the process that is initialized and hasn't initialized yet, for it to be able to manage the process in the system. Now, typically, so this use hash table, so because it uses keys. And another thing is that with keys, for example, you can easily return a value, just like with log structure data table that we discuss in database. In log structure, basically you have a mem table, a memory where you query via key, and that key will query now the disk via segment, and that segment in the disk are actually already compressed. Now, how do you query that efficiently? So you query that by compressing and then having some like background process that will delete the segment, or the segment from time to time, because those segments in the disk add up a lot. And remember, a lookup in a disk is expensive. So the difference with this is that this is working in memory. It's not working in disk, so it's fast. So these typically the keys to this table are identifiers, names of variables, and declarations. So the keys to this table are the name of the variables and the declaration. So that's the identifiers. So because most of the program is a variable, this is what you have as a node uh, parallel to the nodes in your tree. So in that case, we call it a symbol table, and the values it associates with each key tell us what that identifiers refers to. So the value or the declaration are also stored there, but it's not, executed until it is initialized. The most powerful bookkeeping tool is to transform the tree into an entirely new data structure that more directly express the semantics of the code. So if you want those binding from tree, uh, instead of like a key value to a parallel node to it, you can transform this tree to a more uh, similar to the semantics of the user or programmer's code. So back in the days of yore, when front end and back end were coined, compilers were much simpler. Later researchers invented new phases to stop between two halves. Rather than discard the old terms, William Verb and company lumped those new phases into the charming but spatially paradoxical name middle end. So this is the middle end. So that we are talking about the static analysis.